Okay, we'll get started. In this section we're going to be going through 3a and 3b, which is going to be looking at Newton's second law. So the first thing to realize is actually kind of a review of a concept from earlier in science, and that's mass. So mass is the amount of material in an object. So the amount of stuff in something that would be defined as its mass. So mass, with the symbol m, is a scalar. Scalar meaning it doesn't have a direction, it just has a size. So like 5 kilograms doesn't have a direction, scalar. So mass is a scalar that has the standard metric unit of kilograms. So again, 5 kg, 5 kilograms, that's the standard unit. And again, a kilo, 1,000 grams. The next topic, or not topic, but the next term is force. You've probably heard that before, but we're going to define it very precisely. So force, it's going to have the symbol F. That's what causes objects to accelerate. So the reason why objects move and change their velocities is because of a force. And a force is any push or pull on an object. So again, that could be a lot of things, pushing or pulling, but anytime you have a push or pull, that would be considered a force. So force is a vector and has the standard metric unit of newtons. Newtons. And that would be abbreviated with N. So you'd have like 5N, 5 newtons. Or sometimes you might see this notation, kilograms times meters per second squared. Same thing, but typically you'll see the N for Newton. So again, force is a vector, meaning it has a direction and a size. So you could actually draw out the vector. Like right here, this would be the force vector. And in this case it looks like it's going to the right. So again, that's force. This vector is symbolizing a push or pull on that object. So again, the mass of an object, the force on an object. The next thing is an idea called net force. So what net force is it's a sum of all the forces acting on an object. So that's the net force. And it's going to have this symbol right here, this squiggle, F. So the squiggle means net, or the total force. So again, I'll show you quickly. So what that would look like, I'll draw it down here. So if you had the net force of an object, that's just tallying all the forces together. So let's say we had this object, there's 5 newtons this way, and let's say there's 3 newtons this way. If you want to take the net force, you're just adding all the forces together. So what that would be in this case would just be 5 newtons in a positive direction plus 3 newtons, and it looks like a negative direction, left. And then you get your net force out. So again, that's what net force is. It's just adding up all the forces, taking into account their directions. So that's what net force is. You're just summing all of those forces together. The last thing for this section is an equation, and it's going to be called Newton's second law. So this equation relates acceleration to the mass of an object and the net force on that object. So this is the equation right here. So this is the net force. So it basically says the net force. So if you added up all the forces acting on an object, that would be equivalent to that object's mass times that object's acceleration. So it's basically saying all these things are related. How much stuff is in an object and what forces are acting on an object are related to how it's accelerating or how its velocity is changing. So that's really the idea here, is that objects have mass, they can have forces on them, and that we can actually figure out what the effect those forces are going to have with this equation right here. So that's the first part. Let's take a look at the second part. So in the second part, we're going to be looking at how to kind of diagram and classify some of these forces. So the first thing is we have a new term. It's called a free body diagram. Free body diagram, or FBD, free body diagram, is a sketch of an object with all the forces acting on it. So this is a free body diagram right here, actually. And if you look at it, right, it's just a block, basically, and you draw all the force vectors acting on it. So there's, in this case, there's two forces. There's one this way, and there's another one this way. So we're going to look at some of the common types of forces you actually might see, and that would be drawn on a free body diagram. The first is friction, the frictional force. Frictional force, that's abbreviated F, subscript F, so force of friction. That's the force between objects in contact with each other, and that's going to oppose the motion of that object, basically. So for example, if you have an object, and let's say you pull it one way, right, you pull it, let's say you pull it to the left, what's going to happen is there's going to be a force of friction in that other direction, basically. So whatever way you pull something, or whatever way it's moving, the force of friction will oppose that. And the reason for that is that basically the surfaces of objects aren't perfectly smooth, so they're actually going to rub, the surfaces are going to rub against each other, and you're going to get a force that slows it down. So that's pretty common. Unless something's frictionless, which is pretty rare, you're going to have this force. Again, that's really just the surface of two objects interacting with each other. So again, if you pulled something one way, the force of friction is going to act in the opposite direction. So that's the force of friction. The next one is the force of air resistance. Air resistance. And it's going to be abbreviated F air. F subscript air. And that's the force that acts on objects moving through the air. So again, if you throw a ball through the air, as it moves through the air, you're going to have air is actually, the air molecules are actually going to oppose that, and they're going to end up pushing back on that ball a little bit. So you're going to get a force of air resistance acting in the other way. So it's kind of like friction in that whatever way the object's moving, whatever way it's pushed or pulled, you're going to have an opposing force from the air resistance, basically. And the last one is the applied force, and that's just kind of a general term. So the applied force, F subscript A, is a general term used to describe really any push or pull that doesn't really fall into these first two categories. So again, lots of stuff could fall into this. You have a car engine, you push a bookcase across the floor, any kind of generic push or pull is going to fall into this applied force category. So you're going to actually see that a lot. So for this section, just keep in mind a free body diagram, what that is, and that the major types of forces that you're going to see. There'll be others, but for now, just to focus on these three. So now the last thing, we're going to see a problem out with this. So this is a problem you might see. So before I go through it, make sure you take an attempt at solving it first. Again, make sure you're attempting to solve it. If you're stuck, that's okay. Maybe look back in the notes. At least set it up. Maybe draw something. Okay, I'll go through it. So we have is a car traveling west. It has a force of from the engine of 10,000 newtons, and then we have a force of friction of 1,000 newtons. And then it's asking what is the acceleration of the car if we know the mass is 2,000. So let's think about this. Let's see what we have. We know the force from the engine, or the applied force, because that's really just a generic push or pull. There's no engine force specifically. We know that force is 10,000 newtons. We know that there's a force of friction of 1,000 newtons. We know the mass is 2,000 kilograms. And we're looking for the acceleration because it says, what is the acceleration? So these are the knowns. And this would be your unknown. So you don't have to, but it might be a good idea to draw a free body diagram. Just draw a picture of what's happening. So draw your block. And what do we have? We have an applied force. It says it's going west, so if it's going west, that must mean the applied force is west. Right? And then if it says the force of friction, well, it doesn't say which way it's going, but if the applied force is west, if the car is going west, if it's being pushed west, the force of friction is going to try to oppose that. So the force of friction will be opposite. Will be like that. So again, we have forces and we're trying in the mass and we're trying to figure out the acceleration. So the way to relate those would be with Newton's second law. Right? So what we need to do is we need to tally up what is that net force. So let's think about that. We're going to write that out symbolically on the left side. So we have negative, we have the force applied, or the applied force. That's going to be a negative. It's a negative because it's west, right? If we look at this, this is to the west. This would be a negative direction. And then we're going to add that, to add to that the force of friction, positive. You're going to add it, and it's positive because it's in a positive direction. It's equal to m times a, the mass times the acceleration. From right here, we just really have to plug in because we do know FA, FF, mass, and we're looking for acceleration. We do know everything except for acceleration, which we can solve for. So again, right before I do the algebra, make sure, very important that you have this. The knowns, unknown, the diagram, and the equation and the setup first. And then after here, it's really just algebra. So you plug in, was it 10,000 N plus the force of friction 1,000 N is equal to the mass 2,000 times the acceleration. So let's do the math out. This is negative 9,000 newtons. It's equal to 2,000 times A. A would be what? Negative 4.5. Well, I'll write it a little differently. So if you divide 9,000 by 2,000, it's negative 4.5 meters per second squared equal to A. And that's your answer. So again, for this, it looks like a lot is going on, but again, it's really the same idea with knowns, your unknown, and your equation. So make sure you have your notes, make sure you have your problem copied down, and that's it for now.